The Cambrian Explosion, short fuse or long burn?
To the question of why we do not find rich fossiliferous deposits belonging to these periods prior to the Cambrian system, I can give no satisfactory answer.
This quote from The Origin of Species sums up Darwin's greatest dilemma, referring to the obvious void in the Precambrian fossil record.
Around 543 million years ago, all of the modern animal phyla seem to appear in one enormous diversification event. This event is referred to amongst scientists as the Cambrian Explosion. This period of evolutionary radiation took place over approximately 20 million years, which is an extremely short time period relative to the sheer variance seen in the different phyla. If you place the birth of the planet at the beginning of a calendar year, the Cambrian Explosion would run for less than 2 days during November. In this short period, every single modern-day animal phyla would appear in the fossil record.
Darwin's theory of natural selection revolves around the evolution of new life over many millions of years, posing the question as to how this event came about. Suggestions have been made regarding possible environmental changes that could have led to this burst. During the Ediacaran, there was a long period of recurring ice ages in a phenomenon commonly referred to as snowball Earth. When the glaciers melted, large amounts of rock were eroded, pouring a variety of nutrients into the oceans. This allowed for photosynthetic algae to bloom, subsequently increasing the levels of oxygen. It has been hypothesized that this increased oxygen facilitated an advancement in animal metabolism, resulting in increased ecological interactions and complexity, such as the development of predator-prey relationships.
The short fuse theory takes the fossil record at face value, implying that this diversification event began in the Cambrian during favourable environmental conditions. The fossils found in the Cambrian, and indeed modern animal taxa, are incomparable to the soft-bodied specimens seen in the preceding Ediacaran. Appearance of features such as hard skeletons, eyes, and bilateral symmetry in the Cambrian is thought to have led to runaway evolution due to an arms race. Effective predators developed due to these innovations, and consequently, the prey had to evolve defences to keep up.
This goes some way to explaining the sudden abundance of hard structure fossils, such as those found in the Burgess Shale in the Canadian Rockies. Primitive members of many modern phyla were found at this time, including early echinoderm Stromatocystis, arthropod relative and top predator Anomalocaris, and even primitive chordate Picaia gracilens, a worm-like creature with evidence of a primitive notochord, a pivotal innovation in the evolution of vertebrates.
The alternative to this is the slow burn theory, evidence for which lies in the Hox gene clusters. The last common ancestor of protostomes and deuterostomes had Hox genes vital in modern-day phyla, and molecular clock evidence has resulted in acceptance that they predate the Cambrian Explosion, suggesting that the tools to build complex body plans already existed. The new environmental conditions at the start of the Cambrian resulted in greater ecological interactions and therefore allowed the developmental potential of these toolkits to be fulfilled. Minor reshuffling of these genes through traditional natural selection is thought to be the mechanism behind this expansion in morphological diversity.
Trace fossils of soft-bodied organisms show a continuous line of evidence across the Ediacaran and Cambrian boundary. The sudden appearance of new body fossils makes this as an artifact of an increase in preservability because of mineralized body parts like skeletons and shells. In turn, this may simply reflect the changes in ocean chemistry. Dickinsonia of the Ediacaran biota is an example of one of these trace fossils, recently discovered to have been a bolitarian living in the Precambrian, after previous debate about its taxonomy. There have been recent suggestions that these divergences occurred even further back in the Cryogenian, followed by a macroevolutionary lag prior to the Cambrian.
The theory as to how the Cambrian Explosion panned out is not restricted to these two ideas. There is also the possibility that an extinction event occurred on the boundary of the Ediacaran and Cambrian periods. Significant environmental change during this time could have caused the demise of the Ediacaran biota, followed by the radiation of the Metazoans and occupation of the vacant niches.
So what happened? The Cambrian Explosion could well have accounted for a massive diversification in species. However, the view that the genetic tools required for rapid species diversification were already in place before the Cambrian has recently gained traction. Whether the Cambrian explosion followed the short fuse or the long burn model, the event certainly had enormous ramifications for ecological complexity. This diversification is the basis for the variety of life we see today.